All right, Chapter 2, Chemistry Comes to Life. In this chapter, we're going to go over the nature of atoms, chemical bonds and compounds, the role of water in life, and then we're going to move into the major molecules of life. So here we go. Section 1, the nature of atoms. Everything that is on Earth is comprised of matter. The air we breathe, the water we drink, everything that takes up space and has mass is called matter. And all matter exists in one of four states, either solid, liquid, gas, or plasma. And all matter, both living and non-living, is going to be composed of basic substances that we call elements. Now, an element is just a substance that cannot be broken down into a simpler substance by ordinary chemical means. In other words, elements are composed of only one type of atom, and each element has its own unique chemical properties like density, solubility, melting point, reactivity. All of these things are unique for that particular type of atom or that particular type of element. There are 92 elements that occur naturally. However, only 6 elements actually make up 95% of the body weight of all living organisms. These are going to be used with the acronym CHONTS. It's very awkward to say, but it's easy to remember. Carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. The properties of these elements are essential to the unique functions of cells and organisms. So we're going to break this all down a little bit further, starting with an atom. An atom the word is Greek terminology meaning uncut or indivisible. I'm never going to quiz you on Greek roots or definitions or what words mean necessarily, but I feel like having the Greek root helps you understand what words mean, helps you apply them, helps you remember them, helps you understand them in their context. So I will always provide sort of the etymology of each word. Atom, it's Greek for uncut or indivisible. And it's going to be the smallest part of an element that still displays the properties of the element. So whether you have a brick of gold or a single atom of gold, that gold is always going to react the same way. It'll have the same density. It'll have the same solubility. It'll have the same reaction in whatever situation. Whether we're dealing with a lot or a little bit, it's all gold. So an atom is the smallest part of an element that displays the character of that element. And the element and the atom are going to share the same name. So like I said, whether we're talking about a single atom of gold or a brick of gold, it's all gold. So the element and the atom share their name, and it's going to be annotated with a 1 or 2 letter symbol that stands for its name. So although the atom cannot be broken down by ordinary chemical means, it is composed of several smaller building blocks. These are going to be known as subatomic particles. And these subatomic particles are what give characteristics and features to the atoms. And they're going to vary in location, charge, and mass. These are the 3 components or characteristics that I would like you to note for each of the subatomic particles: their location, their charge, and their mass. So there are 3 subatomic particles that are going to be found in every element, and that we are specifically going to be focusing on in this class. They're going to be differentiated by their mass and location, charge, mass, and location. So the very first one that we're going to be talking about is going to be the protons. Protons are ultimately going to be responsible for a lot of the unique characteristics of the element. Gold is gold because it has 79 protons in its nucleus. If it were to only have 78 protons, it would be platinum and no longer gold. What we're looking at right here is an atom of helium. We know it's helium because it has 2 protons right here. 1, 2 protons in its nucleus. So gold is gold because it has 78 protons, 79 protons. Carbon is carbon because it has 6 protons packaged into its nucleus. If it had 7 protons, it would suddenly become nitrogen. So the number of protons is essential to all of the characteristics that make an element unique. So protons are going to be positively charged. They're going to be located inside of the nucleus. They're going to have an atomic mass of 1. Neutrons are going to be found inside of the nucleus as well. Neutrons have no charge. They're found inside of the nucleus. They will also have an atomic mass of 1. Neutrons are neutrally charged. The variations, so although they don't contribute to the overall charge of the atom, they do contribute to some very key characteristics. Variations in the number of neutrons won't change the element itself, but it can lead to radioactive isotopes, which we're going to cover in a moment. So if we change the number of protons, we suddenly change the element itself. If we change the number of neutrons, we change its radioactivity. We change whether or not it's going to be a radioactive element. Now, electrons are going to be our third subatomic particle. Electrons are not going to be found in the nucleus. Instead, they're going to orbit around the outside of the nucleus. They're going to orbit around the outside of the atom. Electrons are very, very small. They have no mass, or their mass is so small it's considered negligible. So electrons are very small. They have an atomic mass of 0, but they do have a charge, and they are going to be negatively charged. The precise location of electrons is very difficult to establish, so their locations are going to be usually indicated using shading or approximated energy shells, because electrons are constantly moving around. So that's why we have, we only have 2 electrons in this atom, but we have them drawn in this sort of shell-like pattern orbiting around that nucleus. It's important to note that the vast majority of an atom is empty space. If this atom were drawn right here as the size of a football field, so picture this whole mass at the size of a football field, the nucleus would be roughly the size of a gumball in the center of the field, and the electrons would be microscopic particles whizzing around in the upper stands. These models are only approximations of where those electrons might be found at any given moment, but keep in mind that they are big. They're whizzing around in the outermost stands, and very tight down in the center of that football stadium is a tiny little nucleus around the size of a gumball. So you're going to see a lot of space-filled models, but I would like you to just kind of keep that in mind. The vast majority of atoms is actually going to be empty space. To help you review, here is a great table that breaks down all of the particles, protons, neutrons, and electrons, where they are located, what their charge is, and what their mass is. So I would like you to be very familiar with this table when you are discussing and or assembling various atoms. So the nature of atoms, as we've already mentioned, each element has a very specific characteristics. And to help us understand or differentiate the different elements, we're going to look at a few characteristics like the atomic number and the atomic mass. Atomic number is going to be the number of protons in an atom of in each atom of an element. So all atoms of the same element have the same number of protons in the nucleus. Like we said before, carbon is carbon because it has 6 protons. If we suddenly had more or less protons, we would not have carbon anymore. So atomic number is the number of protons inside of the nucleus. This is what gives the element its unique properties, and generally atoms are considered to be electrically neutral, meaning that there's an equal number of protons as electrons. So if we have 6 protons in the center of a nucleus, that means we have 6 positive charges. If the atom is going to be electrically neutral, we must also have 6 negative charges to balance that out. Do you guys remember what subatomic particle contains negative charges? And if we needed to balance out 6 protons, how many and what type of subatomic particle would balance out 6 positive charges? All right, so atomic number, the number of protons in a nucleus. Atomic mass or mass number, you'll see it written both ways. The mass number of an atom is equal to the sum of the number of protons and the number of neutrons in the atom's nucleus. It's approximately equal to its mass number. So atomic mass is going to be, if every proton has an atomic mass of 1 and every neutron has an atomic mass of 1, then the atomic mass is going to be that sum total of protons plus neutrons. Typically, when we are looking at an atomic symbol, the atomic symbol is going to be written as a subscript, the atomic symbol is going to be the letter in the center. So here we're looking at a case of carbon-12. Carbon, or the letter C is going to be the atomic symbol for carbon. It's not considered an abbreviation. So when you're writing atomic symbols, you just have to put the letter. Don't worry about putting a period or anything like that. It's not an abbreviation, it's a symbol. So the atomic symbol for carbon-12 is going to be C. And then we're going to write the atomic number down in the lower left-hand side as a subscript. So this is going to indicate, that atomic number, remember, indicates the number of protons in the nucleus. The mass number is going to be written up above. The mass number in this case is 12. If we know that the mass number is the total number of protons and neutrons found in that nucleus, and we have a mass number of 12 and an atomic number of 6, how many neutrons are going to be found in this nucleus? All right. So here is an example of the periodic table. The periodic table is what you're going to use to find the atomic symbol, the mass, and the number for each element. So here is an example over here. We have carbon, which we just looked at. Carbon has an atomic symbol found right here. That's going to be C. We have an atomic number, which is going to be 6, indicating that there are 6 protons inside of the nucleus. And we have an atomic mass of 12, indicating that we have a total mass number of 12 protons and neutrons. So now we're going to talk about what happens when we change that. We know what happens when we change the number of protons. If we change the number of protons inside of a nucleus, we change the nucleus. We change the atom itself. If, however, we change the number of neutrons, we end up with something that's known as an isotope. Isotopes are atoms of the same element that differ in the number of neutrons and therefore have different atomic masses. So here's an example of the carbon atom, as we've already kind of mentioned. The official atomic mass you see on the periodic table is going to be the average mass of all the isotopes for that atom. Since the majority of carbon is carbon-12, meaning that there are 6, and we know that there are 6 protons inside the nucleus of a carbon atom. If there are going to be 6 protons and our total mass number is going to be 12, we know that there must be 6 neutrons. So the majority of carbon found on Earth is going to be carbon-12, meaning that it has 6 protons, 6 neutrons. The atomic mass is going to be, or the averaged atomic mass on the periodic table is going to be much closer to carbon-12 than carbon-13 or 14. And we can see that on the periodic table. I'm going to back up for just a second. On the periodic table, we'll see that the average atomic mass is going to be 12.01, indicating to us that the vast majority of carbon found on Earth is going to be carbon-12, or have 12 subatomic particles in its nucleus. To determine the number of neutrons from an atomic mass, you're going to just subtract the number of protons from the atomic mass and take the closest whole number. So, for example, if we have we know that carbon-13, let me rephrase for a moment. So carbon-12 has 6 protons, and we know that if we take 6 from 12, we end up with 6. We have 6 protons and 6 neutrons in carbon-12. How many neutrons are going to be found in carbon-13? And again, how many neutrons are going to be found in carbon-14? Take a moment to figure that out. Then if you want to determine the number of neutrons in a particular atom, all you're going to do is take a look at the periodic table. And you're going to take your mass number and subtract your atomic number, and you'll come up with a number of neutrons. So in the case of nitrogen, we have a mass number of 14. We know there are 7 protons found inside of that nucleus, so there must be 14 minus 7 is going to be 7.01, or 14.01 minus 7 is going to be 7.01. So we know that there's, rounded to the nearest whole number, there's going to be 7 neutrons in a standard atom of nitrogen.